What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 9, Section 2, Sum and Difference Identities. Let's do it. So question 1 asks to explain the basis for the cofunction identities and when they apply. So I sort of drew out a triangle and I just wrote two of the cofunction identities. And really what it comes down to is it comes down to this idea of complementary angles. And so, y is sine of an angle equal to cosine of the complement of that angle, right? Because imagine if theta is, and I know this is in radians, but imagine if theta was like 30 degrees. So then this would be like 90 minus 30, which would be 60. Hence, 60 and 30 are complementary. So these are complementary angles. So why does this relationship exist? Because if we look at a triangle, if I know that this is 90 degrees and all the angles add up to 180, this angle and this angle are therefore complementary, which means this angle must be pi halves minus theta. Okay, so these two together add up to 90 degrees or pi halves radians. Now, if we look at what is sine of theta in this example, it's opposite over hypotenuse, b over c. What is cosine of this angle, pi halves minus theta? It is adjacent over hypotenuse, also b over c. That is why these exist. That is the basis for the cofunction identities. Boom, done. Explain to someone who has forgotten the even-odd properties of sinusoidal functions how the addition and subtraction formulas can determine this characteristic. So I've got the sum and difference identities here. Now, first of all, when something is odd, like sine is odd, we know that sine of negative x should be equal to negative sine of x. Okay, so let's first start with that. And what I'm going to use to remind myself that sine is indeed odd is I'm going to take my difference formula for sine. Okay, and what I'm going to do is I'm going to take sine of, and I'm going to make the x value 0, and we can just leave that y value as y. Okay, so this is sine of 0 minus y. Now, really, this is sine of negative y. So what we should get on the other side is negative sine of y. So let's see what we get. So we get sine of, and then again, the x value is 0, cosine is y, and then minus cosine of 0, sine of y. Now, sine of 0 is 0, so this goes away. And then cosine of 0 is actually 1. So that just turns into 1, keeping the sine of y, which gives us negative sine y. Guess what? That's what we would have predicted for this to be odd, so that's verification. Now, what about even? For even, like cosine is even, that means cosine of negative x should equal cosine of x. Just like the same thing, but it's almost like the negative on the inside does nothing. Okay, so let's now do the same thing. We'll use the cosine difference formula and see what happens. So same thing, we'll say cosine of 0 minus y, and what we should expect to see is just equals to cosine of y on the other side. So we got cosine of 0, which is x, times cosine of y over here, right? That's the second part, plus sine of 0, sine of y, okay? Sine of 0, sine of y. And I already know sine of 0 is 0, so this whole thing goes away. Here, cosine of 0, that's 1, so that just goes away to 1, but then this stays here. And just like we predicted, cosine of 0 minus y is equal to cosine of y. So that's how you can verify it. That's how you can show it. If you forget, boom, done. So for this one, I'm asked to find the exact value of cosine of pi 12ths, but that's not on the unit circle, right? So what I'm going to have to do is I'm probably going to have to use the difference formula for cosine because pi 12ths is going to be smaller than anything on here. But the good news is that pi 12ths is the same as 3 pi 12ths minus 2 pi 12ths. Okay, why does that matter? Because 3 pi 12ths is actually pi 4ths. That's on the unit circle. 2 pi 12ths is pi 6ths. That's also on the unit circle. So check this out. I'm going to make cosine of pi 12ths the same as cosine of pi 4ths minus pi 6ths. And then now we can use this formula. So let's do that now. So you can see what I've done is this is x, this is y, so it's just like in the formula, cosine of pi 4ths, cosine of pi 6 plus, right? It's flipped when that's minus, this is plus, sine of pi 4ths, sine of pi 6. So now let's evaluate this. So cosine of pi 4ths on the unit circle is the x value, so that's rad 2 over 2. Cosine of pi 6 on the unit circle is rad 3 over 2. Sine of pi fourths is that y value, rad 2 over 2, and then sine of pi 6 is that y value there, which is 1/2. So now on the left-hand side, we get rad 6, right? Rad 2 times rad 3 is rad 6 over 2 times 2, which is 4. Here we get rad 2 times 1, which is rad 2 over 4. And then if we want to consolidate just because they have a common denominator, but we can't combine those, right? It's going to stay separate. We just got rad 6 plus rad 2 over the common denominator of 4. That's how you do it. Done. So for this one, we're trying to take sine of 11 pi 12ths. Now, 11 pi 12ths is not on the unit circle, so again, we're going to have to use the sum formula, okay? And the way we can get 11 pi 12ths from the unit circle is by adding 2 pi thirds to pi fourths, because if we get common denominators, right, that becomes 8 pi 12ths multiplied by 4 over 4. This one multiplied by 3 over 3, we get 3 pi 12ths, right? So then that's how you can add up to that 11 pi 12ths. So now let's use that sum formula and we'll write it out here. So sine of 2 pi thirds plus pi fourths equals sine of 2 pi thirds cosine of pi fourths plus, and then it's cosine of the first angle, which is cosine of 2 pi thirds, times sine now of the second angle, which is pi fourths. Okay, now let's evaluate using the unit circle. So sine, here's 2 pi thirds. Sine is that corresponding y value, which is rad 3 over 2. So it's rad 3 over 2 times cosine of pi fourths. That's right here. That's rad 2 over 2. And then we have plus cosine of 2 pi thirds, which is that x value, which is negative 1/2. And then we got sine of pi fourths, which is also rad 2 over 2, right? Like corresponding y value. Now let's evaluate. So here we have rad 6. Here we have 1 times rad 2. That's rad 2. And then minus, so we'll make it minus rad 2. And then over that common denominator, that's why I'm combining everything to this common denominator of 2 times 2, which is 4, okay? And there's the final answer. Done. So for this one, we got tangent of 19 pi over 12, and we can get 19 pi over 12 by adding these two values in the unit circle, 3 pi fourths and 5 pi 6. And the reason why is because if we got common denominators of 12, this would be 9 pi 12ths. Multiply this by 2 over 2, this would be 10 pi 12. So you see, we come back to this. And now we can use the sum formula for tangent. So as we write this out, we get tangent of 3 pi fourths plus tangent of 5 pi 6 over 1 minus tangent of 3 pi fourths times tangent of 5 pi 6. Okay, let's evaluate that. So tangent of 3 pi fourths, here's 3 pi fourths. Tangent is the y over the x. Since they're both the same except for one's negative, that's going to be negative 1. So we got negative 1 plus, and then tangent of 5 pi 6, that's again going to be y over x. So 1/2 over negative rad 3 over 2. So check this out, 1/2 over negative rad 3 over 2. It's like 1/2 times the reciprocal of that, which is 2 over rad 3. Again, negative. And then the 2's cancel out. We get 1 over rad 3. Rationalize the denominator by multiplying by rad 3 over rad 3, and we get negative rad 3 over 3 over 1 minus, and again, tangent of 3 pi fourths was negative 1, and tangent of 5 pi 6 was negative rad 3 over 3, okay? So just so we can see here, these two negatives are going to cancel out, so it's still going to be 1 minus rad 3 over 3. And on top, we have negative 1 minus rad 3 over 3. Now, just making some room, we're going to consolidate and simplify a little bit further. I'm going to get common denominators, so I'm going to turn that negative 1 into negative 3 over 3 minus rad 3 over 3 over 3 over 3. I'm turning the 1 into 3 over 3 minus rad 3 over 3. Okay, now I can further consolidate. I can say the numerator is going to be negative 3 minus rad 3 over 3, and the denominator is going to be 3 minus rad 3 over 3. Then I can multiply by the reciprocal of this denominator to simplify, which is 3 over 3 minus rad 3. Then these 3's are going to cancel out, and I'm left with negative 3 minus rad 3 over 3 minus rad 3. Now, what they've done in the textbook is they've further rationalized the denominator in this answer by multiplying by the conjugate of this, which is the same as that denominator, but replacing the minus with a plus, like so. Then as I FOIL the denominator, I get 9, 3 rad 3, negative 3 rad 3, they cancel out, and then negative rad 3 times rad 3, which is just negative 3. So we get 9 minus 3, which is 6. And then on top, we get negative 3 times 3 is negative 9. Then we get negative 3 rad 3. Then I get, again, negative 3 rad 3. And then I get negative rad 3 times rad 3, which is negative 3. Okay, so now we can simplify a little bit further. On top, negative 9, negative 3 make negative 12. And then negative 3 rad 3 minus 3 rad 3 is negative 6 rad 3 over 6. Last but not least, we can divide everything by 6, and then we get negative 2 minus rad 3. So there's the final answer. Again, it's equivalent to this. It just depends on what your teacher exactly wants. But if we do want everything nicely simplified, this is the answer. A lot of work, but there you go. Boom, done. So for this one, we want to use the difference formula for sine to make this simpler. So let's do that now. So first we have sine of the first argument times cosine of the second argument, 3 pi fourths. And then we have minus cosine of the first argument times sine of the second argument, 3 pi fourths. And now let's evaluate. So cosine of 3 pi fourths, here's 3 pi fourths, here's cosine. It's negative rad 2 over 2. So we have sine of x, which doesn't change, times negative rad 2 over 2. And then we have minus, and then what is sine of 3 pi fourths? Well, that is the y value. That's positive rad 2 over 2. So rad 2 over 2. And then we have cosine of x that doesn't change. So there you go. That's how you do it. Done. Here we got cosine of x plus 2 pi thirds. So we're going to use this sum formula to simplify. So first I take cosine of the first argument x times cosine of the second argument, which is 2 pi thirds. And then you notice when it's plus here, it's actually minus here in the formula. So then we say minus, and then it's sine of the first argument x times sine of the second argument 2 pi thirds. Now let's use the unit circle and let's evaluate cosine of 2 pi thirds and sine of 2 pi thirds. So here's 2 pi thirds. Cosine is the corresponding x value, so that's negative 1/2. And then we leave the cosine x as is. And then sine of 2 pi thirds, that's that corresponding y value, and which is positive rad 3 over 2. So we got rad 3 over 2. And then that sine of x stays as is. So that's how you do it. Done. So for this one, we're really asked to use the cofunction identities to see what this is equivalent to. And so I put the cofunction identities up here. So secant of pi halves minus theta is equivalent to cosecant theta. So that's all they're testing here. Boom, done. So this is again testing the cofunction identities, and here it is. Tangent of pi halves minus theta is the same as cotangent of theta. So here this would be equivalent to cotangent of x. That's how you do it. Done. So this one is using the tangent difference function to sort of in reverse, right? Because if you look at it, look, it's tangent x minus tangent of y over 1 plus tangent x tangent y. It's the same thing. So we're just going to do this in reverse and kind of bring it back to this format. And I'm seeing that x in my formula is 3/2 x, and I'm seeing y in my formula is the second argument, which is 7/5 x. Okay, now let's put it all together. So it would be tangent of 3/2 x minus 7/5 x. And then what we can do is we can get common denominators and then kind of consolidate. So multiply that by 5 over 5. That's 15 over 10x minus multiply this by 2 over 2, which is 14 over 10x. And that just becomes 1 over 10x tangent, boom, done. So this is saying that given that sine of a is 4/5, cosine of b is 1/3, with a and b both in the interval 0 to pi halves, find sine of a minus b and cosine of a plus b. So I know that sine of a minus b from this formula right here is going to be sine a cosine b minus cosine a sine b. Okay, so that's going to be this right here. And then for cosine of a plus b, that's right here. So that's going to be cosine of a cosine of b, and then it's going to be minus sine of a sine of b. Okay, now we can sort of put this together because I know that a is 4/5. So I know that sine of a is 4/5, cosine of b is 1/3. So let's kind of put this together. So sine of a, that's 4/5, and cosine of b is 1/3. So I'm just going to kind of replace this. Now we have to find cosine of a. They didn't give us cosine of a. So to figure that out, what I'm going to do now is I'm going to draw a little triangle. So when we talk about angle A, okay, sine of A is 4/5, which means sine is opposite over hypotenuse. That means the opposite could be 4 and the hypotenuse could be 5. And then I can find this missing side using Pythagorean's theorem. But we can also recognize that this is a 3, 4, 5 right triangle. Okay, so this has to be 3, but you can verify that with Pythag. Okay, what about B? So for B, it's saying, we'll put B up here as well. B is saying cosine of B is 1/3. That's cosine is adjacent over hypotenuse. So I could say the adjacent side is 1, the hypotenuse is 3. Now using Pythagorean's theorem, I could say 1 squared plus, let's call this side A, or let's call it X actually, just so we don't mix things up. 1 squared plus X squared equals 3 squared, which is 9. Subtract both sides by 1, because 1 squared is 1. X squared equals 8. So this becomes a square root of 8, which simplifies to 2 rad 2. So anyways, now I can use this triangle to find cosine of A. Cosine of A is adjacent over hypotenuse, so that's 3/5. And then sine of B is opposite over hypotenuse. See, the second triangles come in handy. So it's 2 rad 2 over hypotenuse, which is 3. All right, so then this simplifies to 4 times 1 is 4 minus 3 times 2 rad 2, which is 6 rad 2. And that's over that common denominator of 5 times 3, which is 15. So there is this part. Now for the second part, cosine of A again is 3 over 5, and cosine of B, which is what they gave us, is 1/3, minus sine of A, which is opposite over adjacent, or hypotenuse, but they did give us that, which is 4/5, and then sine of B, opposite over hypotenuse, 2 rad 2 over 3, 2 rad 2 over 3. So again, we get a nice common denominator of 15, and then on top we get 3 times 1, which is 3, minus 4 times 2 rad 2, which is 8 rad 2. So that is how you do it. Boom, done. So for this one, we're going to start taking arc cosine and arc sine. Okay, so I got the unit circle up here. So remember, arc cosine is saying for what angle in the unit circle, when we take cosine of it, do we get rad 2 over 2? Remember, cosine relates to x values. So I see a rad 2 over 2 here. I also see a positive rad 2 over 2 here. But we have to remember that the range of arc cosine is from 0 to pi. So this would not be viable. So the answer would be pi fourths. And then what about arc sine of rad 3 over 2? So for that one, sine relates to the y value. So we need to say, hey, where does the y value equal rad 3 over 2? I see it right here. Now, I also see it right here, but that's outside of the range of arc sine, because arc sine is negative pi halves to pi halves, okay? So it's going to be this angle, which is pi thirds. Now we're taking cosine of pi fourths plus pi thirds. Check it out. We can use our nice sum formula, right? So that's the same as taking cosine of pi fourths, cosine of pi thirds, minus, right, it's flip-flop with cosine. When it's plus, then it's minus sine of the first times sine of the second. Now let's use the unit circle again. So cosine of pi fourths is that value, which is rad 2 over 2. Cosine of pi thirds is this value, which is 1/2. Sine of pi fourths is this value, which is rad 2 over 2. Sine of pi thirds right here, and that's the y value, is rad 3 over 2. And now let's simplify everything. We're going to get a nice common denominator of 2 times 2, which is 4. And then on top, we have rad 2 times 1, which is rad 2, minus rad 2 times rad 3, which is rad 6. That's how you do it. Done. So for this one, it says to simplify and then graph the simplified version as well as the original. And you might recognize that this is a cofunction identity, and it's equivalent to simply sine of x. So let's graph sine of x and this and see what they look like. So here's cosine of pi halves minus x, and there's sine of x, and look, it's right on top. So they are the same, they are equivalent. That's how you do it. So here what we're doing is we're going to leverage our cofunction identity, and the cofunction identity says that tangent of x equals cotangent of pi halves minus x. So knowing this, if this is the x in this case, right, or the argument, the angle, whatever, I can substitute this in here and get an equivalent version in cotangent. So it would be cotangent pi halves minus, and then that whole argument, which is pi thirds plus x, okay? So now let's distribute that negative, and we get cotangent of pi halves minus pi thirds minus x. Now let's get some common denominators. Let's get 6. So multiply this by 3 over 3. We get 3 pi over 6. Multiply this by 2 over 2. We get 2 pi over 6. 3 pi minus 2 pi is just pi over 6, and then that minus x just stays there. So this is equivalent to cotangent of pi 6 minus x. Now let's graph this and the original in Desmos. So here's the original tangent pi thirds plus x in red, and then cotangent of pi 6 minus x in blue. It goes right on top, hence showing that they are equivalent. That's how you do it. Done. Here we're going to use our cofunction identities, which states that tangent of x is equivalent to cotangent of pi halves minus x, all right? So in this case, x here, that's this, right? So if I take this argument and I plug it in for this over here, I'm going to get an equivalent expression. So this would be the same as cotangent of pi halves minus, and then it's this whole thing, pi fourths minus x. So let's distribute that negative, and then we get pi halves minus pi fourths plus x, right? The negatives cancel out. And then this I can multiply by 2 over 2. This becomes 2 pi over 4. So 2 pi over 4 minus pi over 4 is just pi over 4. So now we're left with cotangent of pi over 4 plus x like this. Okay, now let's graph these two in Desmos. So here's tangent of pi fourths minus x in red, and here's cotangent of pi fourths plus x in blue. You see they're right on the top of each other. They're equivalent. That's how you do it. Done. Leveraging our cofunction identities, we know that sine of x is equal to cosine of pi halves minus x. And if this is our quote-unquote x, our angle argument, I can plug this in here and get an equivalent expression. So this would be like cosine of pi halves minus, and I'm going to put that whole thing in parentheses, pi fourths plus x. So then we're going to distribute the negative, and then we get cosine of, I'm going to make pi halves into 2 pi fourths. Just multiply top and bottom by 2, minus 1 pi fourths minus x. So then these subtract and combine. 2 pi minus pi is just single pi over 4 minus x. So it becomes cosine of pi fourths minus x. Let's plug this into Desmos and graph both of these and see what they look like. So here's sine of pi fourths plus x. Here is cosine of pi fourths minus x in blue. And you can see they are indeed equivalent. So that's how you do it. Done. So for this one, what they did in the back of the book is they actually used the sum formula to simplify and get an equivalent version. So we're going to do that as well. So this becomes sine of the first argument times cosine of the second argument plus cosine of the first argument times sine of the second argument, which is x, okay? What is sine of pi fourths? That is, here's pi fourths. Sine is the corresponding y value. It's rad 2 over 2. So we got rad 2 over 2 cosine x plus, and then cosine of pi fourths is also rad 2 over 2. It's that x value there. Rad 2 over 2 sine of x. So for some reason in the back of the book, they reformatted this again. I'll show you what how we can get there. But basically, we can get to the answer in the back of the book by multiplying by rad 2 over rad 2. Now, me personally, I would leave it as is. I wouldn't do this because we don't like radicals in the denominators. But this is how we can get there if you want to see how they got it. So then we'd have rad 2 times rad 2 is 2 over 2 rad 2, and we'd get the same thing here, 2 over 2 rad 2, which means those would cancel out, and then we're left with, on over here, sine of x over rad 2. Over here, we're left with cosine of x over rad 2. I just switched the order because, again, this is how it's presented. But like I said, that would work. Also, what we had would work. But let's take this, because it's equivalent. Let's take this and let's take this and let's graph them in Desmos and see what they look like. So in red is sine of pi fourths plus x, and then in blue is the second expression, sine of x over rad 2 plus cosine of x over rad 2. And you can see that they are indeed equivalent. So that's how you do it. Done. So for this one, we're meant to graph it, and we're going to do that using a graphing calculator in Desmos to see if f of x is equivalent to g of x. So let's do that now. So here's the first function, f of x equals sine of 4x minus sine of 3x, and as we kind of move it over, cosine of x, just like how it's presented in the book. And then here's the second function, which is g of x, but here I just left it as f of x again. And when I bring this in blue, look, it's right on top of the red. That means that these functions are indeed the same. Boom, done. So for this one, we're meant to graph both of these functions and see if they are indeed equivalent. So we're going to see that now in Desmos. So here's the red function, and here's the second function in blue. And you can see they're not the same. They don't match up. Okay, so now we have to find an equivalent second function. So let's do that now. So to get our equivalent function, I want to use either a sum or difference formula. And what I'm recognizing is that this sure looks like some sort of, if we kind of look at these two together, it almost looks like our summation formula in a sense, right? Sine of an argument times cosine of a second argument. So I'm going to use that as the basis to sort of derive this. So let's imagine sine of 9x. The reason why this is cool is because I can rewrite this as sine of 3x plus 6x, okay? And then I can use, right, so this is all equal. Then I can use this summation formula to rewrite it. So that would be sine of 3x cosine of the second argument 6x, which is cool because that's that. And then it's plus cosine of the first argument 3x times sine of the second argument 6x, okay? And this is great because this all equals, as we mentioned, sine of 9x. All right. Now, the reason why this is great is because I'm trying to get something equivalent to this, which is right here. So I can isolate this by subtracting both sides by cosine of 3x times sine of 6x. So then I get sine of 9x minus cosine of 3x times sine of 6x. And this equals sine of 3x cosine of 6x. Okay, so they are equivalent. I've just proven that. I've just derived it. So this should be equivalent. Let's graph it in Desmos and check it out. So now here's that original function. Here's what I just derived. And when you look at it, look, it's blue. It's right on top. So therefore, they are indeed equivalent. Boom, done. For this one, we're meant to graph the two functions in Desmos and see if they're equivalent, so let's do that now. So here is sine of 2x, and here is 2 sine x cosine x. You can see they overlap, they're right on top of each other, therefore they are equivalent and the same, done. So for this question, our first objective is to graph both of these and see if they're equivalent. So let's do that now in Desmos. So here we have the two functions. They're clearly not identical. They're clearly not the same. So let's figure out how to get the same. So what I'm seeing here is a double angle identity, but we can also use the sum different identities as well because this is the same as, and I'm going to use x instead of theta. It's the same thing. I'm going to say that tangent of 2 theta or 2x is the same as tangent of x plus x. And now I can use my nice sum formula because then it's tangent of x, tangent of the first argument, plus tangent of x again, tangent of the second argument, which is also x, over 1 minus tangent x, and then again times tangent x. So this simplifies to 2 tangent x over 1 minus tangent squared x. So this should be equivalent, so let's graph it now. So again, here's the first one in red, and here's the second one in blue, and look at that. It goes right on top. They're equivalent, the same, boom, done. For this one first, let's graph them in Desmos and see if they are indeed the same. So when I graph the two together, you can see they are not the same. They are definitely different. So let's see if we can derive the same. So I'm going to actually try and use the difference formula here. And the way I'm going to do is I'm going to imagine that tangent of negative x is the same as tangent of x minus 2x, okay? And now I can use this formula. Let's reformat it or rewrite it now. So it's tangent of the first argument, which is x, minus tangent of the second argument, which is tangent of 2x, over 1 plus, right, with the difference it's actually plus, tangent of the first argument, x, times tangent of the second argument, which is 2x. So now let's see if this is equivalent. So there's the first function. Here is the second function. And look at that, it's right on top. And all we had to do was change that minus to a plus. So these are equivalent, boom, done. So for this one, we're meant to find sine of 195. Of course, that's not on the unit circle, but we can use a sum formula because sine of 195 is the same as sine of 45 plus 150. So why did I choose both of these values? Because 45 is here and 150 is here. I'm choosing values that are on the unit circle. So now let's rewrite it using this formula. So it's sine of the first times cosine of the second plus cosine of the first times sine of the second. Okay, so what is sine of 45? Here's 45. Sine is the corresponding y value, read 2 over 2. What is cosine of 150? Here's 150. Cosine is the corresponding x value. So that's negative read 3 over 2. And then plus, what's cosine of 45? That's the x value of 45, which is also read 2 over 2. And then times sine of 150, that's this y value, which is 1/2. So as we simplify, we get negative rad 6 plus rad 2 over that common denominator of 4. Now we're going to take this in Desmos and verify that this is correct. So here is what we got algebraically. And then, by the way, make sure we're in degrees mode here because this is in degrees. So then we've got sine of 195 just calculated in the calculator. They are indeed equivalent to 4 decimal places. So this is also equal to negative 0.2588, just so we can have it there. But yes, that's how you do it. Done. So for this one, I'm going to actually use the difference formula for cosine because I can make this into cosine of 360. So for this one, I'm going to use the summation formula and I'm going to make it into 300 plus 45. Now, I'm choosing these values because 300 and 45, they're both on the unit circle. So now let's use this nice formula. So first we have cosine of the first argument times cosine of the second argument minus, okay, for the sum formula, it's minus sine of the first argument times sine of the second argument. Okay, now let's see what each of these are. So for 300, okay, cosine of 300 is the corresponding x value, 1/2. Cosine of 45 is again also the x value, rad 2 over 2. And then it's minus sine of 300, that's that negative rad 3 over 2. And then we've got sine of 45, that's that y value, which is, again, rad 2 over 2. Now let's simplify. We get rad 2 minus, and then we have negative rad 3 times rad 2, which is rad 6, but minus negative rad 6 is plus rad 6, and then over the common denominator of 2 times 2, which is 4. So there's the answer. Now let's verify in Desmos. So here's the answer we got. Here's cosine of 345, and you can see that they're equivalent, and to the 4th decimal plate, it's 0.9659, so also 0.9659 for the win. Boom, done. So for this one, we're meant to prove the identity, and I'm going to use the summation formula here. So it's equivalent to tangent of the first argument, x, plus tangent of the second argument, which is pi fourths, over 1 minus tangent of the first argument times tangent of the second argument. So first of all, what is tangent of pi fourths? Well, here's pi fourths. Tangent is going to be the y over the x. And since they're equivalent, that's just going to be 1. So this is the same as tangent of x plus 1 over 1 minus tangent of x times 1, which is just tangent of x. And that is what we have here. So we just verified the identity. Done. So for this one, what I'm going to do is I'm going to use the summation identity for cosine. And we're going to start there and see what that simplifies to. So cosine of a plus b is the same as this right here. So we'd have cosine of a cosine of b minus sine of a sine of b, and that's all over cosine of a cosine of b. Now if I separate this out into two fractions, right, I can say the first part, cosine of a cosine of b over this denominator minus sine of a times sine of b over the same denominator. That's a legal move. I'm allowed to split it up into two different fractions, each having the same denominator. Okay, well, this is obviously the same thing over the same thing, which is just 1. Now, so that's 1 minus, and then what's sine of a over cosine of a? Well, that's the same as tangent of a. What's sine of b over cosine of b? That's the same thing as tangent of b. That's our tangent identity. Tangent equals sine over cosine of the same argument. So we have now verified this identity. Boom, done. So for this one, we're going to start with our cosine addition or sum identity, and that's right here. So we can rewrite that as cosine of x cosine of the second argument, which is h, minus sine of x sine of h. And I just got rid of the unit circle. We don't really need it here, so it's just so I can make more room. And then it's minus cosine of x. All of this is over h. What I'm going to do now is I'm going to group these together because they both have a cosine of x. So I'm going to rewrite this as cosine x cosine h minus cosine x. And I'm going to just separate this out into its own fraction. And then over here, we're going to have minus, and again, it's just going to be sine of x times sine of h over h. Now, this is pretty much what they have here. The only thing is they kind of reformatted it. So what they did is they factored cosine of x out from both of these terms, and then what's left inside parentheses, they didn't have parentheses, but I'll have them here just to make it clear, is cosine of h, and then we pull the cosine of x from a cosine of x, so it's just a 1 left, boom. And then here they just rewrote it with the sine of x in the front like this, and then it's times sine of h over h. And that's exactly what we have on the right-hand side here. So that's how you verify the identity. Boom, done. So this one says prove or disprove the statement. So we're going to use our difference formula right here for tangent and see if they are equivalent. So this is the same as tangent of the first argument minus tangent of the second argument. I hate when they use u and v because they look so similar, but that's okay. Over 1 plus tangent of u times tangent of v. And that looks to be exactly like what they have on the right-hand side. So I would say that yes, this is true. Boom, done. So we're assuming that these three angles are in the same triangle, and then we have to prove or disprove this statement. So we can imagine, it doesn't necessarily have to be a right triangle, but we can imagine that this is A, this is B, and then this is, I know it looks like a Y, but I think it's meant to be gamma, but whatever. We'll just call it Y. And now, since they're all in a triangle, we know that A plus B plus that variable is going to equal to 180. Because all angles in a triangle add up to 180. All three add up to 180. In radians, it would be pi. Okay? So that means that if I subtract y or gamma from both sides, I know that A plus B, alpha plus beta, is equal to pi minus gamma. Okay. Now let's see where we can get with this fact, okay? So I should be able to substitute this in for A plus B. So let's try that now because we already established that those are equivalent. Now let's expand this using our difference formula right here for sine. So it's sine of the first argument times cosine of the second argument, and then it's minus cosine of the first argument times sine of the second argument. Okay. So what is sine of pi? So I don't have the unit circle up here, but if you remember the unit circle, pi is right here. And sine relates to the y value. Well, this is right here on the x-axis, and so it is -1, 0. That's the point. So sine of pi is therefore 0. So this whole thing goes away. What is cosine of pi? Cosine of pi is the corresponding x value, which is -1. So this becomes negative sine of y or gamma. And remember, there's a minus in front of that. So guess what? These end up canceling out to a plus, which means that it is indeed equivalent to this side, right? Sine of A plus B is indeed equivalent to this. So that's how you verify it. It is indeed true. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.